A century after Albert Einstein's 1916 prediction of gravitational waves in his general theory of relativity, physicists have finally confirmed their existence. In another galaxy over 1 billion light-years away, two black holes collided, shaking the fabric of spacetime. Twin laser interferometer gravitational wave observatory, LIGO detectors, on opposite sides of the United States quivered as gravitational waves washed over them. According to Einstein's theory of general relativity, spacetime is a four-dimensional fabric, which can be pushed or pulled as objects move through it. Gravitational waves are propagating ripples in the fabric of spacetime, traveling at the speed of light. Imagine a large boat bobbing in the ocean. Smaller objects, like buoys and lifesavers, bounce up and down too. Space is like the ocean. All the planets, stars, and galaxies are like the boats, buoys, and lifesavers sitting on the fabric of spacetime. While the strongest gravitational waves are produced by catastrophic events, such as colliding black holes and the collapse of supernova, they are millions of times smaller and less disruptive when they reach the Earth. By the time the gravitational waves reached LIGO, the amount of spacetime wobbling they generated was thousands of times smaller than the nucleus of an atom. So even though we can't feel it, gravitational waves in space make the Earth bob ever so slightly. Comprised of two enormous laser interferometers located on opposite sides of the United States, LIGO exploits the physical properties of light and space to detect gravitational waves. As a wave passes, it stretches the fabric of spacetime in a parallel direction and shrinks it in a perpendicular direction. LIGO detects these changes using an interferometer. This instrument splits a single laser beam into two and shoots them in perpendicular directions down two 4-kilometer-long arms. If the beams travel equal distances, ricochet off LIGO's mirrors, and recombine near their sources, the light waves cancel one another and send no light signal to the nearby detector. A gravitational wave, however, stretches one tube while squeezing the other. It alters the distance that each beam travels relative to the other. Because of this difference in distance, the recombining waves aren't perfectly aligned and don't cancel. The detector picks up a faint glow, which signals a passing gravitational wave. Gravitational waves are a new way of seeing the cosmos. Waves from the Big Bang would tell us more about the formation of our universe. Detecting waves from black hole collisions, supernova explosions, and massive neutron stars wobbling would give us new insight into the cosmic events that produce them. The data collected from pairs of black holes will allow physicists to measure the rate at which the universe is expanding and how much dark energy there is in the universe. They are also crucial in proving Einstein's theory of general relativity and could also help physicists determine where the theory goes astray. Finally, gravitational waves could help explain how gravity operates in extreme conditions. These discoveries could lead to a more accurate, all-encompassing model and pave the way for a theory of everything.
Created using Powtoon.